Hello, I've returned to seek more manual repairs on my systems. However, first, I would like to tell you about something very big. Infinity. Infinity is that which is boundless, endless, or larger than any natural number. It is often denoted by the infinity symbol. Since the time of the ancient Greeks, the philosophical nature of infinity was the subject of many discussions among philosophers. In the 17th century, with the introduction of the infinity symbol and the infinitesimal calculus, mathematicians began to work with infinite series, and what some mathematicians, including L'Hopital and Bernoulli, regard as infinitely small quantities, but infinity continues to be associated with endless processes. As mathematicians struggled with the foundation of calculus, it remained unclear whether infinity could be considered as a number or magnitude, and, if so, how this could be done. At the end of the 19th century, George Cantor enlarged the mathematical study of infinity by studying infinite sets and infinite numbers, showing that they can be of various sizes. For example, if a line is viewed as the set of all its points, their infinite number, i.e. the cardinality of the line, is larger than the number of integers. In this usage, infinity is a mathematical concept, and infinite mathematical objects can be studied, manipulated, and used just like any other mathematical object. The mathematical concept of infinity refines and extends the old philosophical concept, in particular by introducing infinitely many different sizes of infinite sets. Among the axioms of Zermühl-Fraenkel set theory, on which most of modern mathematics can be developed, is the axiom of infinity, which guarantees the existence of infinite sets. The mathematical concept of infinity and the manipulation of infinite sets are used everywhere in mathematics, even in areas such as combinatorics that may seem to have nothing to do with them. For example, Wiley's proof of Fermat's last theorem implicitly relies on the existence of large, very large, infinite sets for solving a long-standing problem that is stated in terms of elementary arithmetic. In physics and cosmology, whether the universe is spatially infinite is an open question. The history of infinity. Ancient cultures had various ideas about the nature of infinity. The ancient Indians and the Greeks did not define infinity in precise formalism, as does modern mathematics, and instead approach infinity as philosophical concept. Early Greek. The earliest recorded idea of infinity in Greece may be that of Anaximander, circa 610 to 546 BCE, a pre-Socratic Greek philosopher. He used the word aprion, which means unbounded, indefinite, and perhaps can be translated as infinite. Aristotle, 350 BCE, distinguished potential infinity from actual infinity, which he regarded as impossible, due to the various paradoxes it seemed to produce. It has been argued that, in line with this view, the Hellenistic Greeks had a horror of the infinite, which would, for example, explain why Euclid, circa 300 BCE, did not say that there are an infinity of primes, but rather prime numbers are more than any assigned multitude of prime numbers. It has also been maintained that in proving the infinitude of the prime numbers, Euclid was the first to overcome the horror of the infinite. There is a similar controversy concerning Euclid's parallel postulate, sometimes translated, if a straight line falling across two other straight lines makes internal angles on the same side of itself whose sum is less than 2 right angles, then the 2 other straight lines being produced to infinity meet on the side of the original straight line that the sum of the internal angles is less than 2 right angles. Other translators, however, preferred the translation the 2 straight lines if produced indefinitely, thus avoiding the implication that Euclid was comfortable with the notion of infinity. Finally, it has been maintained that a reflection on infinity, far from eliciting a horror of the infinity, underlay all of early Greek philosophy, and that Aristotle's potential infinity is an aberration from the general trend of this period. Zeno, Achilles and the Tortoise. Zeno of Elea, circa 495 to circa 430 BCE, did not advance any view concerning the infinite. Nevertheless, his paradox, especially Achilles and the Tortoise, were important contributions to in that they made clear the inadequacy of popular conceptions. The paradoxes were described by Bertrand Russell as immeasurably subtle and profound. Achilles races a tortoise, giving a latter a head start. Step 1. Achilles runs to the tortoise starting point where the tortoise walks forward. Step 2. Achilles advances to where the tortoise was at the end of Step 1, while the tortoise goes farther yet. Step 3. Achilles advances to the tortoise was at the end of Step 2, while the tortoise goes yet further. Step 4. Achilles advances to where the tortoise was at the end of Step 3, while the tortoise goes yet further, etc. Apparently, Achilles never overtakes the tortoise, since, however many steps he completes, the tortoise remains ahead of him. Zeno was attempting to make a point about infinity. As a member of the Eleatics school, which regarded motion as an illusion, he saw it as a mistake to suppose that Achilles could run at all. Subsequent thinkers, finding this solution unacceptable, struggling for over 2 millennia to find other weaknesses in the argument. Finally, in 1821, Augustin Louis Cauchy provided both a satisfactory definition of a limit and a proof that for 0 less than x less than 1, a plus ax squared plus ax cubed plus ax to the fourth plus ax to the fifth plus ... equals a divided by 1 minus x. Suppose that Achilles is running at 10 meters per second. The tortoise is walking at 0.1 meters per second, and the latter has a 100-meter head start. The duration of the chase fits Cauchy's pattern with a equaling 10 seconds and x equaling 0.01. Achilles does overtake the tortoise. It takes him 10 plus 0.1 plus 0.001 plus 0.00001 plus ... equals 10 divided by 1 minus 0.01 equals 10 divided by 0.99 equals 10.10101 ... seconds. Early Indian. The Jain mathematical text Shura Prajnati, 4th to 3rd century BCE, classifies all numbers into 3 sets: innumerable, innumerable, and infinite. Each of these was further subdivided into 3 orders: innumerable, lowest, intermediate, and highest; innumerable, nearly innumerable, truly innumerable, and innumerably innumerable; infinite, nearly infinite, truly infinite, infinitely infinite. 17th century. In the 17th century, European mathematicians started using infinite numbers and infinite expressions in systematic fashion. In 1655, John Wallis first used the notation, infinity symbol, for such a number in his De Sectionibus Concis, and exploited it in area calculations by dividing the region into infinitesimal strips of width on the order of 1 divided by infinity symbol. But in Arithmetica Infinitorum, also in 1655, he indicates infinite series, infinite products, and infinite continued fractions by writing down a few terms or factors and then appending ampersand c, as in 1, 6, 12, 18, 24, ampersand c. In 1699, Isaac Newton wrote about equations with an infinite number of terms in his work De Analysi per Equationis Numero Terminorum Infinitas. Mathematics. Hermann Weyl opened a mathematico-philosophic address given in 1930 with Mathematics is the science of the infinite symbol. The infinity symbol, sometimes called limniscate, is a mathematical symbol representing the concept of infinity. The symbol is encoded in Unicode at U plus 221E. Limniscate, infinity, parentheses, ampersand, infin, semicolon, parentheses, and in LaTeX as /INFTY. It was introduced in 1955 by John Wallis, and since its introduction has been used outside mathematics in modern mysticism and literary symbology. Calculus. Gottfried Leibniz, one of the co-founders of infinitesimal calculus, speculated widely about infinite numbers and their use in mathematics. To Leibniz, both infinitesimals and infinite quantities were ideal entities, not of the same nature as appreciable quantities, but enjoying the same properties in accordance with the law of continuity. In real analysis, the symbol limniscate called infinity is used to denote an unbounded limit. The notation x approaches infinity means that x increases without bound, and x approaches negative infinity means that x decreases without bound. For example, if f of t greater than 0 for every t, then the integral from a to b of f of t dt equals infinity means that f of t does not bound a finite area from a to b. The integral from negative infinity to infinity of f of t dt equals infinity means that the area under f of t is infinite. The integral from negative infinity to infinity of f of t dt equals a means that the total area under f of t is finite and is equal to a. Infinity can be used to describe infinite series as follows. The summation of f of I starting at 0 to infinity equals a means that the sum of the infinite series converges to some real value. The summation of f of I starting at 0 to infinity equals infinity means that the sum of the infinite series properly diverges to infinity in the sense that partial sums increase without bound. In addition to defining a limit, infinity can also be used as a value in the extended real number system. Points labeled positive infinity and negative infinity can be added to the topological space of the real numbers, producing the 2-point compactification of the real numbers. Adding algebraic properties to this gives us the extended real number. We can also treat positive infinity and negative infinity as the same, leading to the 1-point compactification of the real numbers, which is the real projective line. Projective geometry also refers to a line at infinity in plane geometry, a plane at infinity in three-dimensional space, and a hyperplane at infinity for general dimensions, each consisting of points at infinity. Complex analysis. In complex analysis, the symbol infinity called infinity denotes an unsigned infinity limit. X approaches infinity means that the magnitude of x grows beyond any assigned value. A point labeled infinity can be added to the complex plane as a topological space giving the 1-point compactification of the complex plane. When this is done, the resulting space is a one-dimensional complex manifold or Riemann surface, called the extended complex plane or the Riemann sphere. Arithmetic operations, similar to those given above for the extended real number, can be also defined, though there is no distinction in the signs, which leads to the one exception that infinity cannot be added to itself. On the other hand, this kind of infinity enables division by 0, namely, z divided by 0 equals infinity for any non-zero complex number z In this context, it is often useful to consider meromorphic functions as map into the Riemann sphere, taking the value of infinity at the poles. The domain of a complex function may be extended to include the point at infinity as well. One important example of such function is the group of Morbius transformations. Non-standard analysis. The original formulation of infinitesimal calculus by Isaac Newton and Gottfried Leibniz used infinitesimal quantities. In the second half of the 20th century, it was shown that this treatment could be put on rigorous footing through various logical systems, including smooth infinitesimal analysis and non-standard analysis. In the latter, infinitesimal are invertible, and their inverses are infinite numbers. The infinities in this sense are part of the hyperreal field. There is no equivalence between them as with the Cantorian transfinities. For example, if h is an infinite number in this sense, then h plus h equals 2h and h plus 1 are distinct infinite numbers. This approach to non-standard calculus is fully developed in Keisler, 1986. Set theory. A different form of infinity are the ordinal and cardinal infinities of set theory, a system of transfinite numbers first developed by George Cantor. In this system, the first transfinite cardinal is Aleph null, the cardinality of the set of natural numbers. This modern mathematical conception of the quantitative infinite developed in the late 19th century by the works of Cantor, Gottlob Frege, Richard Dedekind, and others, using the idea of collection or sets. Dedekind's approach was essentially to adopt the idea of one-to-one correspondence as a standard for comparing the size of sets, and to reject the view of Galileo, derived from Euclid, that the whole cannot be the same as the part. However, see Galileo's paradox, where Galileo concludes that positive integers cannot be compared to the subset of positive square integers, since both are infinite sets. An infinite set can simply be defined as one having the same size as at least one of its proper parts. This notion of infinity is called Dedekind's infinity. The diagram to the right gives an example, viewing lines as infinite sets of points. The left half of the lower blue line can be mapped in a one-to-one manner. Green corresponds to the higher blue line, and, in turn, to the whole lower blue line. Red corresponds. Therefore, the whole lower blue line and its half have the same cardinality, i.e., size. Cantor defines two kinds of infinite numbers, ordinal and cardinal. Ordinal numbers characterize well-ordered sets, or counting carried on to any stopping point, including points after an infinite number have already been counted, generalizing finite and ordinary infinite sequences which are maps from the positive integers leads to mapping from ordinal numbers to transfinite sequences. Cardinal numbers define the size of sets, meaning how many members they contain, and can be standardized by choosing the first ordinal number of a certain size to represent the cardinal number of that size. The smallest ordinal infinity is that of the positive integers, and any set which has the cardinality of the integer is countably infinite. If a set is too large to be put in one-to-one correspondence with the positive integers, it is called uncountable. Cantor's views prevailed, and modern mathematics accepts actual infinity as a part of the consistent and coherent theory. Certain extended number systems, such as the hyperreal numbers, incorporate the ordinary finite numbers and infinite numbers of different sizes. Cardinality of the continuum. One of Cantor's most important results was that the cardinality of the continuum C is greater than that of the natural number Aleph null. That is, there are more real numbers than natural numbers. Namely, Cantor showed that C equals 2 raised to Aleph null greater than Aleph null. The continuum hypothesis states that there is no cardinal numbers between the cardinality of the real and the cardinality of the natural numbers. That is, C equals Aleph 1 equals Beth 1. This hypothesis cannot be proved or disproved with the widely accepted Zermoli-Fraenkel set theory, even assuming the axiom of choice. Cardinal arithmetic can be used to show not only that the number of points in a real number line is equal to the number of points in a segment of that line, but also that it is equal to the number of points on a plane and indeed in any infinite dimensional space. The first of these results is apparent by considering, for instance, the tangent function, which provides a one-to-one correspondence between the interval negative pi divided by 2, and r. The second result was proved by Cantor in 1878, but only became intuitively apparent in 1890, when Giuseppe Pinot introduced the space-filling curve, curved lines that twist and turn enough to fill the whole of any square or cube or hypercube or finite dimensional space. These curves can be used to define a one-to-one correspondence between the points on one side of a square and the points in the square. Until the end of the 19th century, infinity was rarely discussed in geometry except in the concepts of processes that could be continued without any limit. For example, a line was what is now called a line segment, with the proviso that one can extend it as far as one wants, but extending it infinitely was out of the question. Similarly, a line was usually not considered to be composed of infinitely many points, but was a location where a point may be placed. Even if there are infinitely many possible positions, only a finite number of points could be placed on a line. A witness of this is the expression the locus of a point that satisfies some property singular, where modern mathematicians would generally say the set of the points that have the property plural. One of the rare exceptions of a mathematical concept involving actual infinity was projective geometry, where points at infinity are added to the Euclidean space for modeling the perspective effect that shows parallel lines intersecting at infinity. Mathematically, points at infinity have the advantage of allowing one to not consider some special cases. For example, in projective plane, two distinct lines intersect in exactly one point, whereas without points at infinity, there are no intersection points for parallel lines. Some parallel and non-parallel lines must be studied separately in classic geometry, while they need not be distinguished in projective geometry. Before the use of set theory for the foundation of mathematics, points and lines were viewed as distinct entities, and a point could be located on a line. With the universal use of set theory in mathematics, the point of view has dramatically changed. A line is now considered as the set of its points, and one says that a point belongs to a line instead of is located on a line. However, the latter phrase is still used. In particular, in modern mathematics, lines are infinite sets. Infinite dimension. The vector spaces that occur in classical geometry have always a finite dimension, generally 2 or 3. However, that is not implied by the abstract definition of a vector space, and vector spaces of infinite dimensions can be considered. This is typically the case of functional analysis, where function spaces are generally vector spaces of infinite dimensions. In topology, some constructions can generate topological spaces of infinite dimensions. In particular, this is the case of iterated loop spaces. Fractals. The structure of a fractal object is reiterated in its magnifications. Fractals can be magnified indefinitely without losing their structure and becoming smooth. They have infinite parameters and can have infinite or finite areas. One such fractal curve with an infinite parameter and finite area is the Cauchy snowflake. Mathematics without infinity. Leopold Kronecker was skeptical of the notion of infinity and how his fellow mathematicians were using it in the 1870s and 1880s. This skepticism was developed in the philosophy of mathematics called finitism, an extreme form of mathematical philosophy in the general philosophical and mathematical schools of constructivism and intuitism. Physics. In physics, approximations of real numbers are used for continuous measurements, and natural numbers are used for discrete measurements, i.e. counting. Concepts of infinite things such as an infinite plane wave exist, but there are no experimental meanings to generate them. Cosmology. The first published proposal that the universe is infinite came from Thomas Digges in 1576. 8 years later, in 1584, the Italian philosopher and astronomer Giordano Bruno proposed the unbound universe, and on the infinite universe and the worlds, innumerable suns exist, innumerable Earths revolving around these suns in a manner similar to the way the 7 planets revolve around our sun. Living beings inhabit these worlds. Cosmologists have long sought to discover whether infinity exists in our physical universe. Are there an infinite number of stars? Does the universe have infinite volume? Does space go on forever? This is still an open question of cosmology. The question of being infinite is logically separate from the question of having boundaries. The two-dimensional surface of the Earth, for example, is finite, yet has no edge. By traveling in a straight line with respect to the Earth's curvature, one will eventually return to the exact same spot one started from. The universe, at least in principle, might have a similar topology. If so, one might eventually return to one's starting point after traveling in a straight line through the universe for long enough. The curvature of the universe can be measured through multipole moments in the spectrum of the cosmic background radiation. To date, an analysis of the radiation pattern recorded by WMAP spacecraft hints that the universe has a flat topology. This would be consistent with an infinite physical universe. However, the universe could be finite, even if its curvature is flat. An easy way to understand this is considering two-dimensional examples, such as video games, where items that leave one edge of the screen reappear on the other. The topology of such game is toreadal, and the geometry is flat. Many possible bounded flat possibilities also exist for three-dimensional space. The concept of infinity also extends to the multiverse hypothesis, which, when explained by astrophysicists such as Michio Kaku, posits that there are an infinite number and variety of universes. Also, cyclical models posit an infinite amount of Big Bangs, resulting in an infinite variety of universes after each Big Bang event in the infinite cycle. In logic, an infinite regress argument is a distinctively philosophical kind of argument purporting to show that a thesis is defective because it generates an infinite series when either form A, no such series exists, or form B, where it exists, the thesis would lack the role, e.g., of justification, that is supposed to play. Computing. The IEEE floating point standard IEEE 754 specifies a positive and a negative infinity value, and also indefinite values. These are defined as the result of arithmetic overflow, division by zero, and other exceptional operations. Some programming languages, such as Java and J, allow the programmer an explicit access to the positive and negative infinity values as language constants. These can be used as greatest and least elements, as they compare respectively greater than or less than all other values. They have uses as sentinel values in algorithms involving sorting, searching, and windowing. In languages that do not have greatest and least elements, but do allow overloading of relational operators, it is possible for a programmer to create the greatest and least element. The infinity value may still be accessible and usable as the result of certain operations. In programming, an infinite loop is a loop whose exit condition is never satisfied, thus executing indefinitely. Arts, games, and cognitive science. Perspective artwork uses the concept of vanishing points, roughly corresponding to mathematical points at infinity, located at an infinite distance from the observer. This allows artists to create paintings that realistically render space, distance, and form. Artist M.C. Escher is specifically known for employing the concept of infinity in his works in this and other ways. Variations of chess played on an unbound board are called infinity chess. Cognitive science George Lakoff considers the concept of infinity in mathematics and science as a metaphor. This perspective is based on the basic metaphor of infinity, BMI, defined as the ever-increasing sequence 1, 2, 3, ... And this is all to say that, yo mama's so fat, she is bigger than infinity.